Welcome back to Management Decision Tools. In this section, we'll discuss the second set of generalized category problem that we want to be familiar with so that we can quickly deploy the standard template model and focus our energy and time on the specific customizations. Right, so we are going to seek efficiency, and to do that we need to recognize the pattern in assignment problems. So what are assignment problems? We've seen that before earlier on in our discussion about thinner tailoring, right? So we had 4 garments and 5 tailors to have each tailor work on each garment worked on by one and only one tailor. So that would be assigning the garments to the tailors for completion. So typically, when we generalize it, it will be that we have a set of tasks. And because tasks are either given by our boss, supervisor, customers, so they have to be done, right? They have to be done. So we demand that workers be deployed to work on them. On the other side of the problem will be that there is a set of workers. There are workers for us to deploy, and luckily we have a choice. We ought to have more workers, more standby workers to work on our customers' problem than otherwise, because it means that if you have lesser workers to match the tasks, that means some tasks are not being done, and so the customer, that boss of yours, might not be happy about it. So if we have workers, then the question is, how do we assign the workers? Now, clearly, in the case of, say, army, where 5 soldiers and 5 chores: wash the windows, clean the toilet, sweep the floor, clean the cupboard, and tidy up the beds, for example. Soldiers are assumed to be able to do all these, and it doesn't quite matter, how they do it, and so long as they complete it nicely. So we might just randomly assign, and that's okay. That's okay. So randomly assign the workers, the soldiers, to work on the problems, the cleaning tasks, and it doesn't quite matter how you optimize it, because ultimately it is roughly the same. However, there can be dollars and cents involved in more commercial settings, and you want to um, seek an overall cheapest solution in terms of appointing workers to task. It could be 5 projects that you have, and you have 5 vendors, 5 suppliers. Each supplier is fully capable to work on any of the projects. However, of course, the quotation given to us would be different for each project. So each supplier is asked to quote for each of the 5 projects, and when we receive that 25 costings, we compare the 5 costings for each project, might be ranked in terms of being cheapest and most expensive. Yeah, they wouldn't be the same. And of course, it'll be a problem if they are the same, right? So there may be collusion or something. So the question is, how do we appoint or delegate the task or match the tasks so that the overall cost to us will be the cheapest? Okay, so that's always the problem statement. Now, a few things that perhaps we can sort of help ourselves here. I like to put in, of course, assign, right? Whenever we see the word assign, that has to be a nice trigger to say that we have an assignment problem. How about matching? All right. If we hear the word match, if your supervisor asks you to, can you match these tasks with our team? Can you make a schedule of who is to do what? Remember last time in the initial discussions, when we talk about schedule, it is who, what, where, when, how, right? Who does what on what machine by when, and all that. Yeah, so here is specifically who out of these set of machines or workers or supervisors are to be matched with, right? So come up with a schedule, right? So these words all give us a sense that should we be thinking of assignment problem here, right? Because it sounds like that's what our customer, our situation needs. So assign, match, schedule, right? When we come up with a schedule, we need to think about assignment. Um, Basically, these are the words that might guide us, right? So of course, when we hear of transportation, we will think about transportation. So let's look at how we might draw a picture, right? So a picture of assignment should involve tasks and workers. So we have three tasks here and three workers here. We call them agents. And of course, in general, as I sort of verbally gave you this vendor working on project, giving us quotation, right? This example, the vendors will not quote the same cost to us. And so the CIJs will be different for vendor 1 to work on task 1, 2, 3, than vendor 2 to work on tasks 1, 2, and 3, right? So if we compare C11, C21, and C31, we'll find that the cost, there should be some kind of a range. They will differ. So how do we assign supplier 1 to work on which task and 2 and 3 to work on which task? That's assignment. So at the end of the day, we should have a pairing. That is, 1 is to be paired with 2. 2 is to be paired with 3. 3 is to be paired with 1, or some other combinations. So the question is how. So the how part can be translated into an LP model by having, for example, the question on not quantity, but whether should I or should I not. So should I or should I not assign agent 1 to task 1? All right, so that's one question, and it is binary. It is yes, no, it is to do or not to do. So we have that as our decision variable. And of course, if that's the case, we will immediately duplicate it 9 ways to each and every possible assignments. Right? Should we or should we not appoint agent 2 to work on task 1, and so on. So immediately we have m by n number of decision variables, all of which are binary. But let's kind of turn our head around a little bit, because this increasingly looks like a transportation problem, doesn't it? Because so long as the network diagram matches, it will be the same problem. That's the beauty of abstracting everything else, throwing away all the lingos about factory and agents, destination and task. When we draw it out in a network representation like this, it will tell the bare bones story behind, right? So if we draw the assignment network representation and it looks like a transportation problem, then we say it is transportation problem, and we immediately remember, we have learned from previous discussion that if we recognize the problem, pattern recognition, that it is transportation problem, then we immediately whiz out the transportation problem template, copy and paste, and edit it a little bit to customize to the location, to the situation. So why is this a transportation problem? I mean, we can see it from the network representation, but does it make sense in reality? Because we are not having lorries and trucks, right? So the idea is this: the transportation is kind of just a statement, just a virtual activity. To be true to the word assignment, it is basically find a pairing. And to be true to the assignment problem category, it is to find the set of pairings such that the overall cost is the minimum, and that has the same cost and goal as transportation problem. So I like you to think of yourself as an icon here, right? So we are this icon. This worker 1 is an icon. We say, should we transport him over so that he can work on task 1? Okay, let's rephrase our assignment problem like a transportation kind of wording. Should we transport worker 1, agent 1, over to task 1's virtual locality so that this agent 1 can work on task 1? That's our X11. Still a binary question, but let's say